So if you can see that, let me get out of the way so you can see. You can't see it, can you? You might have seen it from the back there. This is a visualization of real data. So it's not real photographs, but it's the positions of nearby galaxies in the universe, which have been mapped by something called the Sloan Digital Sky Survey, and then put into a computer, and this is a visualization of a fly through the local universe. As I say, it's not real imagery, but it's real positions of things, a real map of where we are relative to the rest of the things we can see in the night sky. And every point of light, or little snowflake or dandelion seed in this animation, is a galaxy. So each one of those points of light is an island of, between 100,000 million and anything up to 1,000,000 million or 1,000,000,000,000 stars like our sun, most of which we now know have solar systems around them and planets. So you're looking at rivers and streams and flows of galaxies here. There are of order, we think, around 350 billion of them in the observable universe, and we have very good evidence that the observable universe extends way beyond that and may in fact be infinite in extent. But it's a remarkable thing to think that each one of those is about the size of the Milky Way galaxy, our local island of stars. And those are the institutes that gathered that data. So when I say we want to understand why the universe is the way it is, how it came into being, we're talking about explaining a vast area with a vast amount of stuff in it. As I said, that wasn't a real photograph, but it was real data. Just to drive that home, this is a real photograph. And if you can see this, it's a photograph called the Hubble Extreme Deep Field Image. So this is the photograph taken by the Hubble Space Telescope of a piece of sky you would cover if you took a 5-pence piece and held it about 30 metres away. So imagine taking a 5-pence piece and holding it about 30 metres away. You cover a small piece of sky. The Hubble Space Telescope took a picture of that piece of sky over weeks and weeks and months, and in fact years and years. It was a piece of sky that was chosen, by the way, because it was not particularly interesting from the point of view of someone on the ground. So there are no bright stars or galaxies in that piece of sky. But this is the image the Hubble took. And you see that it's full of structure. In fact, every point of light in this image, except about 2 of them, are galaxies. And this is a real photograph. There are over 10,000 galaxies in this image. The most distant of them, over 13 billion light years away, which means the light from some of the galaxies in this image began its journey to Earth before the Earth had formed. The Earth is only about 4.5 billion years old. So the light was more than halfway to the Earth, travelling at 186,000 miles a second before the Earth formed. So again, the point is, and you see it vividly in this picture, the universe is a big place. So how can we possibly begin to get a handle on how it came into being? Well, actually, the story that we have of the universe, the origin and evolution of the universe, is quite easy to explain. We've measured the age to the time when it was very hot and dense. Said it's 13.798 plus or minus 0.035 billion years, which is one of the great measurements in the history of science. And it's expanded and cooled ever since. And what we found, I'll show you some of the experiments in a moment, what we found is that really when the universe began, it was an extremely simple place. It was a hot, dense place, but simple laws governed the way the universe behaved. And those laws are still the laws that govern the way the universe behaves today. But the universe has got more complicated as it evolved. So today we live in an old and cold and complicated universe with things like human beings and planets and stars and galaxies in it. So the real challenge is to understand how it could be that this complexity, I suppose, crystallized out in a sense. And one way to think about it is that you imagine a snowflake in the palm of your hand. Then it's a very complicated object, a beautiful object. Every snowflake is different. But if you heat the snowflake up, then it melts into a pool of water in in the palm of your hand, and you see that underlying all that complexity was nothing more complicated than H2O, molecules of water, hydrogen and oxygen stuck together. And in the same sense, what we've discovered is that's the story of the universe. As the universe cooled down and expanded, complex things like us almost crystallized out. And I'll tell you a good example of that, which is something called the Higgs particle, or the Higgs mechanism, towards the end of the talk. But I just thought I'd give you one glimpse into the way that theoretical physics works. Because you might say, well, it's one thing saying, well, how did this universe evolve? How do you know all this stuff? And one of the best examples, I think, of the power of just thinking about science and asking actually really simple and naive questions that we might all ask. And one of the best examples is the way that that kind of simple thinking was turned into a powerful idea in the hands of Albert Einstein, who's sat there. It's worth talking about Einstein for a couple of minutes, because this year is the 100th anniversary of his theory of gravity. And you might say, well, why is gravity? How can it be that gravity is a theory that tells us something about the origin and evolution of the universe? Well, I'll try and give you a little insight into that for a couple of minutes. But the remarkable thing probably about Einstein developing his new theory of gravity was what set him off on that road, because it was a simple observation and the attempt to understand it. And I want to show you a video of what the simple observation was. Einstein did this in his mind. So he didn't have an experiment like the one I'm going to show you, but he just sat there in his office, apparently, having a little think one day in Switzerland. And he looked up across the road and he saw someone working on a roof on a building opposite. And he thought, I wonder what happens if that guy falls off the roof. Then he won't notice that he's fallen off until he hits the ground, when he'll notice quite powerfully that he fell off the roof, because he'll land in a heap on the ground. But on his way down, it seems to me that if he didn't look at everything flying past him, he would feel just fine. He'd just be floating down or falling down towards the ground. Now, couple that with an observation of how things fall, and you get Einstein's inspiration for a new theory of gravity. So how do things fall? Well, if you'd seen, I did this for a BBC series the other year, so you might have seen it, or you might not. But this is a demonstration of how things fall when you take the air away, all extraneous forces away, and just watch gravity as it really is. So this is an experiment we did in a vacuum chamber in Ohio, which is owned by NASA. It's the biggest vacuum chamber in the world. It's way bigger than this building, and you can pump all the air out of it, and then you can drop things under the action of gravity to see how they behave. So what we did was the classic experiment of dropping a feather and a bowling ball. And I thought I'd show you this, because if you haven't seen it, again, you can't see it, can you? But most of you can see it. It's a remarkable thing. So this is in slow motion, a feather and a bowling ball, just operating, dropping under the action of the force of gravity with no air resistance. From probably about the height of this building, actually. And you see that if you know some physics, you're doing GCSE, A-level physics, you'll know what the answer is, that things fall